Hi class, today we're going to learn how to solve for different variables for angled projectile motion. Yesterday we went through some of these notes. I'm going to finish them off today. You're going to use your packet in front of you, or you can get it from the sub if you forgot to bring it. And we're going to finish up these notes, and then you're going to use these notes to solve for the second worksheet in that packet that you have in front of you. We started off by launching a marble at a speed of about 7.47 meters per second at an angle of 35 degrees. So I'm going to go ahead and draw the things we know about this object. So this is a marble launcher that's launching a marble, so I can go ahead and say that it has an angled velocity, which I'm going to call v, and that's going to equal 7.47 meters per second. Now what we learned in class is that we can make a right triangle right here. Let me make that a little more horizontal. So we can make our right triangle right there. And our angle theta, which is 35 degrees, that's right there. So what we can do is we can break apart our velocity into horizontal and vertical components. This right here, this vertical arrow, we're going to call that Vy0. That is the initial vertical speed. That is how quickly that marble is rising the instant it leaves the marble launcher. And then we also have Vx, which is going to be the constant speed, the horizontal speed of the marble as it launches out of the launcher. Now, the first thing we're going to want to do for all these problems is solve for the horizontal and vertical velocities. And we took some notes on that already yesterday. So it turns out that the horizontal velocity is Vx, and that's v times the cosine of theta. And the reason is because this right here, that horizontal component, that is the adjacent leg of that triangle, and adjacent goes with cosine from SOHCAHTOA. So we can go ahead and we can do 7.47 times the cosine of our 35 degree angle, and for Vy naught we can do v sine of theta since it's the opposite leg. And we can get those two velocities. Which is 6.12, and the other one is 4.28. So I'm going to write that in. So this right here is 4.28 meters per second going upwards, and this is going to be 6.12 meters per second going to the right. All right, so once we have that, we should also notice a couple other things here. We know what gravity is. Gravity is going to always be negative 9.8 meters per second squared. We should also know that the very top of its flight, the velocity in the vertical direction is 0. Now it still has a horizontal velocity, that's why it still moves to the right, but vertically it doesn't gain any more speed. It starts to actually increase its speed downwards. So for the smallest instant possible, the vertical velocity is 0 meters per second. This occurs at half the time, halfway through. We also have the object landing right back where it was launched from, the same height, I should say. So over here, it also has two velocities. It has a downward velocity and a horizontal velocity. This horizontal velocity, Vx, is the same as the initial one because things in motion stay in motion and we have no air resistance, and horizontal velocity is constant. Now here, which I'll call Vyf because that's the end, it's right about to hit the ground, that's going to be the same as the vertical velocity. So it's going to be 4.28 meters per second, but because it's pointing downwards, I'm going to make that negative 4.28 meters per second. Those are all the givens. That's everything we know. So we know the initial velocity. We can break that up into its components of vertical and horizontal. We know that gravity is negative 9.8. We know that at its maximum height, the vertical velocity is 0, and that occurs at half the time. Knowing that allows us to solve for the rest of the problems. So when it says determine the total flight time of the marble, we're looking for one of the equations up here at the top of your worksheet that has time in it along with all the other givens. And if you wanted to take a few seconds and pause your video right now and search for it, you could. I'm going to go ahead and just tell you what formula it is. Turns out we can use VYF equals VY naught plus A times T. So we know our final vertical velocity is negative 4.28. Our initial vertical velocity is positive 4.28. Gravity is negative 9.8. And our time is what we don't know. So when we do the algebra on this, we get 0.87 seconds. So that is the time for the marble to leave the marble launcher and land at the same height from what it was released. So 0.87 seconds. Determining the range, delta x, how far away it lands, that's really easy. We only have one equation for delta x, and that's our constant speed formula, vx times t. So we can just take our horizontal velocity, which we know from part B above here, that's 6.12 meters per second, times the seconds that it's in the air, which we just found out was 0.87. So 6.12 times 0.87 is 5.32 meters. So in class, if we didn't already test it, I should be able to place a little bucket 5.32 meters away from the marble launcher, and I should be able to launch it, and it should be able to land inside of that bucket. The last thing is determining that maximum height, which is figuring out what is that height from right there, I'll keep going right all the way there, which we will call delta y, our change in height. If you look, we have two equations for it. We have this delta y equation, and we have this delta y equation. And it turns out at this point, we can use both. I'm going to go ahead and use the first one, but I'll do the second one as well at the end. So we can go ahead and we can do delta y equals Vy naught t plus 1/2 AT squared. So I can do delta y equals 4.28, but the time that I'm going to use is not 0.87 seconds. The reason why is because that time is to get all the way to the other end. We only want to know half that time because that's when it reaches maximum height, is when it's halfway through. So I'm going to use 0.87 right here, and I'm going to divide that by 2, and that'll get me about 0.44 seconds. So that's why I'm using the 0.4 instead of the full time of 0.87. So at this point, you would go to your calculator, like I'm doing right now. And we should get a delta y of 0.93 meters. You can also use that other equation, okay? I'll kind of put this over here. If you want to use the VYF squared equals Vy naught squared plus 2a delta y, that's fine. You can use that equation. You just got to make sure that your VYF right here is 0. It's the velocity, the final velocity, when we're looking at the maximum height. So you cannot use the negative 4.28. You have to use Vy when the object is at the maximum height. So that would have to be 0. And if you do that, you should get very close to 0.93 meters. Because of rounding, it might be a little bit off, but you should be pretty close. One last thing. In your homework, it also asks you randomly to solve for like a height, maybe like right here. Like how tall is that? How high is that going to be at that point? So I can go ahead and show you guys how to do that. You would probably want to use, I'll kind of make a little box over here so you guys can do that. You probably want to use the delta y equation right there, Vy naught t plus 1/2 AT squared. We already know delta y, so that's good. We already know gravity, A, that's negative 9.8, so that's good. We just need to solve for the time. So to be able to solve for that, what I'm going to have to give you is I would have to give you that distance there to there. Okay? And doing that, you could do delta x equals Vx times t. And then you could solve, because you would know delta x, this will be given, so maybe I say that that is 3 meters away. You already know your Vx, which is 6.12. And then you could solve for your time. 3 divided by 6.12, and you get 0.49 seconds. So then you could take this 0.49 and you could plug it in there, and you could plug it in there. So I think it's the second problem on both sides of your homework. It asks you to solve for that height at a different location, a location that's not at maximum height or the furthest distance away. And this right here that I just showed you in this little box is going to be that method to do that. All right, I hope that's enough information. Again, I'm here in school today. If you have any questions, you can go ahead and email me, and you want to finish up the front and back of that attached worksheet, and we will talk about it and go over it tomorrow. I'll see you soon. Bye.